Awesome. Good morning. Not an easy session to start, to be at 8:30 here after traffic, but we'll do our best. My name is Daniel Chadash. I'm the co-founder of the DNA Data Storage Alliance, and I work at Twist as a senior director of business development and product management in the DNA Data Storage division. Joel Christener made those slides and led the groups, made most of the slides. I wanted to give him credit for all the work that he did in this group and continue doing. So this is for Joel. He couldn't attend today, so I'm presenting. Want to start, these links will be in the presentation after you'll get it, so it's helpful to background reading and about the topics that I'm going to discuss. So what are we going to discuss today? We'll start to explain the similarities and the differences between DNA and the traditional media that you probably all know. We'll talk about the technical work group, the DARS group that we started, and it's in really good shape now. And talk about a few more details and the status and where we are in terms of our work, and give you a small summary. Let's start. So this is an architecture, a high-level architecture of an SSD. For the ones who don't know, this looks like we have all the storage in the right side. We have a controller. We have a host interface logics that interfaces with the operating system. And from the operating system side, they kind of don't care what happens on the right side. It's all managed by the SSD controller. And this makes it easier for the operating system to work with storage devices. This happens more on the software layer. Again, this is like inside the host interface logic. You can see that the work that the SSD drivers and the SSD software is making is for the operating system to have a much easier and standardized access to the storage unit. I wanted also to look at tape, because tape is more similar to DNA than SSD in a way that the storage media is disconnected from the controller. It stays like that. It has like a barcode in tape, and in tape we also have some kind of a physical structure that is different from DNA. But in a similar way, it's kind of an offline media that you need to connect to a device in order to read. A bit of background on DNA for people that are new to this. So basically, when we talk about DNA data storage, the basic unit that we are working with is called an oligo. An oligo is what you see on the right side. And basically, it's a chain of nucleotides, and those base compounds are A, C, T, and G. These are the bases of DNA. This is like the ones and zeros of computers, okay? And basically, they form like this strand by attaching two strands together, two oligos together, or the complementary oligo. And this is building the DNA strand as we have it today in nature. And basically, an oligo example, as I show at the bottom, you can see it's just a sequence of letters of A, T, G, and C. This is like a one strand. If we'll have a DNA like found in nature, you'll see the opposite strand. So for A, there is a T, for G, there is a C, and it's basically like a double-stranded one. And the concept of storing data on DNA is built from 6 steps. And how do we do it? We basically take any file, any type of digital data, and we convert it to DNA. We do it first with a coding, with a codec that takes the ones and zeros and convert them into A, G, C, and T. We do a step of synthesis. This is making the transition from the digital world to the physical world by creating those oligos. And then we put those oligos in a storage container. And once we want to read the data back, the step between 3 and 4, it can be years, hundreds of years, or minutes whenever we need the data back. We open that container. We do a process called sequencing, which takes from the physical world to the digital world by reading the DNA and producing us a lot of reads, like huge amounts of data of like reads on what the sequencer saw on this material. And from that, we're able to convert to A, G, C, and T and back into the ones and zeros back to the digital file. So this is a high-level concept of how it works. Where is the problem, though? So the difference with DNA is that we don't have the physical structure and organization like we have in tape or in SSD or in hard drives. We don't have a controller. We don't have a built-in kind of a device that can interface with the operating system and kind of give the information and make it easier to consume. And there's no addresses in the memory because there is not a physical separation and not a physical layout. We don't have addresses also in the memory. In addition to that, there are many codecs on how to do this transition from ones and zeros to A, G, C, and T. It might seem simple that we say 0, 0 will translate to A, 0, 1 will translate to C, 1, 0 will translate to G, and so on and so forth. But right now, and so early in the development, we see so many knowledge and IP being built in the codec because there is a lot of error correction and detection, there is compression, there is security. And what happens now is that the codecs are proprietary. It's not like LTFS, that it's kind of like a known way to do it, and basically all the devices, they implement it, and everyone is using LTFS, and the operating system knows how to work with LTFS. Here, it's still like very early on, and the codecs are proprietary. So when we have a DNA storage device in our hands, we are not sure which codec was used in order to encode it, and we must know that in order to decode it back. And we also encountered the issue that DNA should stay more than 100 years. Like the archive should last like more than 100 years, and there are many issues with that because the technology is evolving and you need to be prepared for new technologies in the future that you have no idea what they would look like. You have companies that will go away. Like no one can assure us that a company that writes now a DNA storage archive will be there in 100 years in order to read it back. So you need to plan for it in the codec and in the standards to be able to accommodate that as well. This is where we come into place in this technical group. So a bit of background, the DNA Storage Alliance was formed in 2020 with the idea that we want to build standards in this industry so it won't be fragmented. We want to build the ecosystem to work well with each other, especially when DNA storage is not like one device that is contained and have like a standard interface outside. We have different manufacturers for writing, for reading, for storing, and we want to make sure it all plays together nicely. And part of the alliance was, one part was to do market education and marketing activities to raise the awareness of this new format and media. But the other part of the alliance is to create this specs and standard in order to make it like a great ecosystem, an interoperable ecosystem. And this is one of the groups. We have a few more groups. If you're interested and you're part of SNIA, you can, of course, join us and apply. And this group came to tackle that problem of how do we boot an archive? How do we take an archive that we have no idea who wrote it, which codec was used, and how do we start reading it? So it's basically like an archive boot sector. In different media, it has different names, but the idea that in traditional media, the controller knows where to start. The controller knows whether it's a specific address, whether it's the start of the tape. It's a very known way on how to do that. And we kind of need to define something like that for DNA. And as we said, we don't have linear addressing, we don't have controller, and there is no file system. So how do we do that? So when we go to an SSD, basically, the controller goes to the EEPROM and read the information about the hardware configuration, all the details that are needed. And there is an ECC to make sure that this data is read reliably. You go into block 0, and then you can load the firmware in order to start the controller and start to read and know where to get to. So yeah, in DNA, we don't have this controller. We need to discover the metadata about who wrote it and which codec was used. And basically, what you see on the right, this is a very, very high-level view and kind of like illustrative view of what happens in a DNA archive. So what you see here on the right is a lot of like small segments. These are the oligos that I talked about them before. in a DNA archive, you can think of it, there are billions of them. It's not just like 20 or 30 or something like that. And the goal was to kind of like think what would be a way in order to get the data from the archive with the challenges that I said about, that I talked about before. And so we put that as our goal, and we want to be able to identify the codec, that is how the data was encoded in the rest of the archive, like all the green oligos, how were they encoded. And we also didn't want to block innovation. We didn't want to say there is only one codec to do it, and the standard says you must use this codec, okay? Because we know that companies care about the codec, and there is a lot of innovation to do there. So we wanted to separate the codec of the archive itself, then the codec of this boot sector, the archive, the metadata. And we also wanted a way to provide fast access to the metadata, because in DNA, for people that don't know, it's not as fast as SSD or hard disk drive or tape in the ability to read the data fast. And sometimes you just want to know what's in the archive and not read the whole archive. You don't want to spend hours just to find out that the file that you're looking for is not there. So we also want to do it like in a small way that like it can also be accessed fast, and I'll talk about how we did that. As we took few assumptions in order to be able to do this work. We said that at the time of reading the archive, we say that the document of the specification is available. So if we want to give specific bits of information that are found in the spec, we assume that it is available. We assume that at least the boot record is built from the natural bases of DNA, which is A, G, C, and T. There are technologies today that are looking at adding more synthetic bases into the archive or into DNA, but this is proprietary technology. So we said we want at least the metadata and the boot sector to be standard according to what nature has developed, and not with the synthetic bases. But we still wanted to allow innovation. So if companies want to use synthetic bases and bases that don't appear in nature, they can still use it as long as the boot sectors they write in a standard way. And we assume that the reader at the time of reading will have some form of internet connectivity. And that the DNA will primarily be used as a write-once media. So when we looked at that, this is a famous quote by Will, we can solve any problem by introducing an extra level of indirection. So the problem space is how we go from zero understanding of the archive to an understanding of how to consume the archive. This is the big problem that we faced, and we divided it into two steps. Step one, we wanted to create a mechanism to just understand who wrote the archive and which codec was used in order to code the second step, which is, we call it this is the sector 0, and the second step is sector 1. So do a small step, understand how sector 1 is written, and then read sector 1, and to be able to understand how the rest of the archive was written. So let's talk about the first step. So sector 0. So basically, we don't have any information about the archive. We just have this metal container that I showed before, and we have no idea which company wrote it and which codec was used. So the concept was to fit all the information of sector 0 into a single oligo. The idea behind doing a single oligo is that we don't need to encode using a codec. So the concept of a codec is I take a file of 3 megabytes, and these oligos are only shorter. These oligos are 200 letters or 300 letters. So I cannot write the whole data in one oligo. I need to divide it into very, very large amount of small oligos. And this is why I need a codec, because I need a way to mark those oligos, number them, have error correction and detection in them. So then I involve a codec and it becomes more complex. If we go on a single oligo, we don't need a codec for it because we know how to find this oligo, and then we read the data from it. And this was the idea behind the sector 0, to keep it small as one oligo. Basically, we use things that are called primers. You see them, the blue ones on the left and on the right. Primers are used in order to amplify or take an oligo out of this big pool of oligos that I showed before. Okay, so if I have billions of oligos and I use primer, I can amplify or take out only specific oligos from that pool. And basically, if I can ensure that the blue ones are unique to sector 0, and this is why we need a standard, because then we tell the industry, please don't use this reserved sequence of the blue sequence because it is reserved for sector 0. So then anyone can use these kind of like blue attachments, we call them primers, in order to amplify and take out the sector 0 and read it. This is the concept on how to make it kind of like to find this like initial start in the big archive. And then after we have those primers, basically we have left around 70 bases. We divide it into two 35 base strings. The left one is the vendor, the right one is the codec for sector 1. And Joel built an API service that is currently available on AWS, and basically you can send this string to that service and it will give you back the vendor and the codec that was used, at least the codec version or codec details. And the way to handle errors, if there are, is because we separate the vendor IDs that are way far apart from each other, that you can use the similarity between the sequence provided and the sequence of the vendor in order to find the right vendor with the Levenshtein distance and the people who know these algorithms. And this is just a screenshot of the codec, of the API service. So let's say we found the vendor and we found the version of the codec. Okay, so if it's a public available codec, then you can just go and get the codec details. If it's not a public available codec, you know which company it is and you have the contact details of that company in the spec. So in the spec, we put all the vendors with their IDs and their contact details. And then you can contact this vendor and ask for details on how to read the rest of the archive. But in case it is a public codec for the sector 1, then this will be kind of the standard on what will be inside sector 1. So the idea of sector 1 is, as I said, to have an understanding of what's in the archive. It can be a description of the contents, it can be the time step, when it was written, who wrote it, more details about who wrote it. It can be the parameters that we want to transfer to the sequencer, to the device that reads the archive, on how to read it in the most efficient way. And it's important in DNA because the reading costs money and it's time consuming, so you want to have it as efficient as possible. Basically, we had, I wouldn't say a significant amount of data, but it's a decent amount of data to allow us to have all this information, and we use JSON as the representation. So because it doesn't fit on one oligo, this is why we need a codec for it, and this is why this codec is defined in sector 0. But we still wanted to keep it small because we also wanted to allow the people that build the archive writer, to be able to access it in a different way, not only by reading the DNA. So as long as we keep it as like a few thousands of bytes, we can still encode it in a barcode, QR code, or NFC on the archive itself in a physical way. And this is important because let's say that you have a lot of these capsules, let's say thousands of them, and you want to read fast to understand which one you want, and you lost the way of your catalog or whatever to know which capsule is what. And those capsules are small. You cannot just put a sticker on them, a big sticker that contains all this information. Then we allow this in order to be able to read it fast with a barcode reader or with NFC. So this is how the sector 1 looks like. It's built from a lot of oligos, and they have also a specific primer. You can see this blue one here. That's also a reserved sequence that we defined in the standard. So we basically asked 2 reserved sequences not to be used on the rest of the archive, which I think it's a legitimate request, and a thing that their archive writers can cope with. And then we kind of read all those oligos, and it contains all the ECC information and the codec information in order to rebuild the sector 1. So here you see what we write over there. We can give details on how to sequence it, of the codec, timestamp, some optional fields, and who wrote it. And this is what we did in sector 1. So where we are with it. So both of those specs have been approved by the TA governing board and the technical working group. We're currently in the IP review stage. We're about to publish the specs by end of this year. That's the plan. So a bit of summary. So we have like very interesting challenges with DNA. I touched only on one of them, on how to boot the archive and how to start it, but there are many interesting ones, and you'll hear about them in this in the lectures today, the talks today. So the group is super interesting in what we do. We face like new challenges that were not in the traditional media. So as I said, what we are trying to do in this group is really to go from 0 to be able to read the rest of the archive. And yeah, and like it's a work that's been done for a year and a half almost, and is about to conclude soon, which is kind of the first, I think, spec and standards that comes from the Storage Alliance, which is really, really exciting to see it coming and forming. And of course, thanks to SNIA, we can do this kind of umbrella to develop specs and standards that we couldn't do before. So that was very helpful to us. And yeah, that's it. Happy to answer questions. Any questions? Was it too complicated? Yeah. Yeah. So the question was that on larger files, the archive has like billions and billions of oligos. And then how can we make it the reading to be fast and efficient when we have so many small subunits? So the reading in DNA is not sequential. It's not that we read one by one and move slowly like that. It's kind of like in parallel. So we kind of read the whole thing, we put it, and based on the reading device, some can do millions, some can do more, and it really depends on the device. But you do it in parallel, and then you amplify all of them, and then you build this file from reading all the oligos. There are techniques today of doing random access to the archive. So basically, if I go here, so we can think of the archive just like sector 1. It's built from a lot of oligos, but if you nest primers and you add more primers, and then you can define few areas of the archive. So I can first start with amplifying, just like I amplify only sector 1, I can only amplify only the first part of the archive, or only a specific folder, let's say. So the goal of the sector 1 metadata was also to transfer the information to the sequencer to say, only amplify or only read this part of the archive and not the whole thing. So it kind of can give like a tree of files, sector areas, whatever you want to call it, because it's not really like that in the DNA. But it can say that for the first gigabyte, the first terabyte, use these primers. For the second terabyte, use these primers. And this is how you can make it more efficient and only take some part of the archive and then put it in the sequencer. Yeah. Thank you.
Okay, this question might be a little on the technical but we recently rewrote some software that was encoding, I think it was either graphitol or organicitol fountain, right? It's a codec for
yeah.
And we recognize that the software are dependent upon the random number compiler provided at runtime, right? So the codecs are actually very specific, like exactly what computer you run them on and exactly when you run them. So if I'm understanding this right, so in your sector 0, you have the sequences for the vendor, and you have the sequences for the code. So for codecs that have that many like specific parameters, are you going to create a new sequence for every like that details all of that information? Is that where that information would be contained? Yes.
Yeah. So that's a great question, and this is why we wanted to kind of say you can mention if the codec that is used for sector 1 is proprietary or not. Okay, so I think on public codecs, we won't have as many revisions as we'll have like if private companies are doing like many iterations that they need to change the codec version. But basically you have 35 bases which can accommodate like, I think hundreds of thousands of versions of codec. And we took that into account by thinking that companies might want to iterate and have new versions of the codec, and we'll need new versions in this standard. Sure. Yeah.
Do you have an idea of how much data you can store in sector 1?
The question was if we have an idea of how much data we can store in sector 1. So it's basically, we don't have a limit over there, but we want to limit it because we want to allow to encode it also in a physical way. But basically there is not much limit. Like a company can decide that they want to do like a huge data in sector 1, and then they say we don't care about physical representation of it in a QR code. Okay, because like, I don't know, they put an NFC chip and it can contain a lot of data, so basically they can do, because we allow the optional fields and the ability to insert as much data as you want over there. We think a best practice would be to keep it short and to be able to represent it in a physical way as well. Does this answer the question? Okay. Sorry? Okay. Any other questions? Okay. Awesome. Thank you very much. In case you are interested to join the TA or this group, you're welcome to come to me or to Dave here that will stay through the conference and can hear more details. Thank you. Yeah, we can have a quick break and so I give you some time.